check the calendar. Today is April 6th. Wow. Welcome to Monday, April 6th, as we are once again stuck at home, but presenting a nice presentation for everyone today. Welcome, everybody. Today, we are going to start off this week talking about Tyrannosaurs, the king of the dinosaurs, as lots of people like to refer to them. And so I pulled out, this is actually one of my toys from when I was a kid. And you can see that I had dogs when I was a kid as well, because this foot is missing and it's all chew marks. And I swear those aren't my chew marks, that's dog chew marks, as is his hand. You see his hand is missing there. He's been through some stuff, but we still have him. Actually, at some point, I can't remember if it was my sister's toy first, because her name is written underneath here, or if it was my toy and then later I gave it to her. But either way, it's here now. You can see it at some point. One or the other of us also gave it some lipstick at some point. So some good history on this specimen. I don't think real Tyrannosaurs wore lipstick, but maybe our guest speakers today can let us know whether that's true or not. But either way, we're going to be talking about not just Tyrannosaurus rex, which is the most famous species of Tyrannosaur, but there's actually a whole group of animals called the Tyrannosaurids from quite a few million years. Just Tyrannosaurus rex is kind of the most famous and the biggest of those. And so our guest speakers today are Dr. Denver Fowler and Dr. Elizabeth Freedman-Fowler, both of which work at the Badlands Dinosaur Museum in Dickinson, North Dakota. Elizabeth also works at Dickinson State University, there in Dickinson as well. So we'd like to thank them for being here today to show us some of the specimens they have, including maybe they'll give us a sneak peek of a new Tyrannosaur specimen that they've been working on. So I'll pass it off to them. Denver and Liz, thanks for joining us today.
Hello. Hi. Yeah. Welcome to Dickinson, North Dakota. I should probably start by saying that our museum has been closed for a number of weeks, so I just turned the lights on for the first time in a while. We can still come in here, but we're not open to the public. But we thought we'd show you some things that we've got here in the galleries, and then we were going to go back into our storage area and look at some of our new trends. So this is the lobby of our museum, and sat behind me right now is the skull of a T.rex. This is a copy of a skull. T.rex was the largest and last of the Tyrannosaurs. It's the most famous, and I think it was the first one that was described, at least described from well-known domain. So this is one that's the real one is on display in Los Angeles County, California, where you can see it's losing a fight against the Triceratops. So this one was found in the 1960s by a chap called Harley Galvan. And it's actually one of the biggest T.rex skulls that's been found. There's a couple that are bigger, I think, now. The biggest one we think is at the Museum of the Rockies, and there's Scotty in Saskatchewan in Canada. And then this one was originally found in Montana, and this is what people's classic sort of view of a Tyrannosaur, huge carnivorous reptile, carnivorous dinosaur. So there's a few features you can see on this. Can't tell what I'm seeing. That are typical of tyrannosaurs that makes them fairly unusual as carnivorous dinosaurs. One is the huge wide teeth. Tyrannosaurs, most carnivorous dinosaurs have quite narrow teeth, a bit like knives for slicing and cutting through flesh. But tyrannosaurs, and Tyrannosaurus especially, has really wide, fat teeth. And we'll talk a little bit about what we thought it was doing with those later. Another thing that's quite interesting about tyrannosaurs is that they have, tyrannosaurids, is that they have little horns, these bumps on the top of the skull. And they often have a rough patch on the top of the nose. And we think that these were for display, for showing off to other tyrannosaurs. So Tyrannosaurus rex lived in North America between about 67 and 66 million years ago, the very last of the Tyrannosaurs. We're going to go into the main exhibit in a few minutes. I don't know if I was going to talk too much about where Tyrannosaurs came from, how they evolved. I've got some pictures of some of the earliest known Tyrannosaurs. So we're quite familiar with Tyrannosaurus rex from the very end of the Cretaceous period, 67 million years ago. But there are some ancestors of T-Rex that lived much longer ago. And the oldest ones are known from places like China, but also from parts of Europe. Actually, where I'm from, England, has a number of dinosaurs that we've only really recently found or only recently realized are ancestors of Tyrannosaurus. So Tyrannosaurus is famous for being huge and one of the biggest carnivores that ever lived. But the ancestors of Tyrannosaurs were actually quite small. I have a little picture of one here. So this is a very old paper from 1910. And this is a picture of a skull. Can you get that on camera?
Yeah, I got it.
So this is actually the skull of one of the oldest known tyrannosauroids. Originally, when it was found, they thought it was closely related to Megalosaurus. And in fact, only very recently, in the last 15, 20 years, have they realized that this animal, which is actually called Proceratosaurus bradleyi, is a primitive tyrannosaur. And one of the features of early tyrannosaurs, this is the eye, these are the teeth, obviously, and the snout. You can see this little bump here. Well, one of the features of early tyrannosaurs is they have a big bump, a big crest on the tip of their nose. And that's one of the reasons why this dinosaur was originally called Proceratosaurus, because they thought it was closely related to an American dinosaur called Ceratosaurus. But it wasn't. It's actually a very early tyrannosaur. So this is from the late Jurassic, I think, or the middle Jurassic, about 160 million years ago. So 160 million years ago, Tyrannosaurs were small. They were only about 1 to 2 meters long. They were the same size as little rat duck, if you think about from some of the movies. And they didn't become large until almost the very end of their time. As we go through from the Jurassic into the Cretaceous, you see more kinds of early tyrannosaurs. They lose the big nose crest that we saw on that one, and they get a more sort of flat head, and they start to look a little bit more like a typical tyrannosaur. And some of those are called, there's one called Eotyrannos from the early Cretaceous of England, about 130 million years. And then in the middle Cretaceous, about 100 million years ago, still the biggest carnivorous dinosaurs are things like Allosaurus, and well, not Allosaurus, but animals related to Allosaurus. And only once they go extinct did tyrannosaurs get the opportunity to get larger. So let's move into our exhibit space. Okay, so this is an Allosaurus. This isn't a Tyrannosaur. And Allosaurus, for a long time, was one of the largest carnivorous dinosaurs. This is from the end of the Jurassic period, about 150 million years ago. Now, Allosaurus looks very similar to Tyrannosaurs, but of course, there's a few things that are different. One of the obvious things is that it has 3 fingers on the hand, whereas Tyrannosaurids famously have 2 fingers on.
They're really big fingers too.
But around the time Allosaurus was living in North America, there were small tyrannosaurs, one of which is called Stokesaurus. We don't have very much of these dinosaurs. I think another is called, Tannicalagrius. There's another early tyrannosaur species from North America. I didn't want to look at Allosaurus too much, so we'll move along a little bit. So this is more what people think about as classic Tyrannosaurs. So this is a mounted skeleton of a dinosaur which is labeled as Albertosaurus, but it's probably something called Gorgosaurus. This is a Tyrannosaur. I would call it an ancestor. A lot of people don't like to use the word ancestor, but we know that all dinosaurs had ancestors. So this one was probably an ancestor of one of the larger tyrannosaurs. This one lived about 76 million years ago, and most of the remains of Gorgosaurus are from Canada. There are a few remains that are known from Montana. We're actually going to see some new ones that we've been digging up in a few minutes. So this is the classic shape of a tyrannosaur. It's got a relatively short tail actually for a carnivorous
Yeah, we can
dinosaur.
compare this to Allosaurus because they're right next to each other. There, Allosaurus is a really long tail. Right.
And it has two-fingered hands with small claws. It has a relatively large head, but Gorgosaurus hasn't yet got quite as fat round teeth as the Tyrannosaurus that we saw before. So this animal lived about 76 million years ago, 10 million years before T.rex. So I actually don't work on the evolution of Tyrannosaurs very much. Most of what I do on Tyrannosaurs is looking at things like their behavior and seeing what sorts of information we can get about Tyrannosaurs from their bones. So one of the things that we have here in Dickinson, when I got here 4 years ago, one of the fossils that we had on display was a leg of a T.rex. So this is a leg. It's a real leg. We actually have the whole leg, but a couple of the bones. So this is the shin bone called the tibia. These are the foot bones. And then these are the toes at the bottom. I don't know if you can see the laser pointer on the screen. Maybe I should have brought my incredibly powerful laser pointer, which is.
Well, somebody watching him on a full screen.
So anyway, this is the tibia, the shin bone. And we also have the upper leg bones called the thigh bone, the femur. And then there's another little bone that goes here called the fibula. So a couple of years ago, we came into the sandpit here. We carefully lifted up those leg bones and we put them on a trolley and took them to our lab. And then we carefully put them onto a table outside. We got a great big diamond saw and we cut big chunks out of the middle of those bones. And you might not be able to tell by looking at this bone in the sand, but we've actually cut a chunk out of this bone, this middle bit here. That's not real. The rest of the bone is real, but we copied the piece that we cut out and we glued it in. So why would we want to cut out the middle of a leg bone of our T.rex? Well, I'm going to hand you over to Liz to talk a little bit about why we would want.
So one of the things that I work on with another of our friends, Dr. Holly Woodward in Oklahoma, is looking inside of dinosaur bones. So we cut out a piece of them and then we grind them up very thin so we can look at them under a microscope. When you do that, all right, so this is not a T.rex, this is a duckbill, but it would look very similar. Okay, so this is the shape of the cross section of the bones. We take one of the leg bones and we cut it. There's a hollow space in the middle for the bone marrow. And then all around the outside, it's kind of like tree rings. So we can see lines every year as the dinosaur grew. So we can count up how many years old it is. And this is the only way to know the age in years of a dinosaur. How many years old was this particular one when it died? So that's what we're doing with our T.rex as well. And it's really cool. If you zoom in even more, you can see the individual cells of the dinosaur bone. So this is a zoomed in one. So there's little lines that represent blood vessels. And then there's it's hard to see on the picture, but where there's an arrow, every arrow is just like a tree ring. That's how many years old it is. And these teeny tiny black spots that look like little ants in the background, those are called osteocytes. And those are the cells that lived inside the dinosaur's bone. There's all sorts of cool things we can learn about how they grew and how they live by looking inside.
Okay, so that's basically what we want to do with our Tyrannosaur. We want to find out how old it was when it died and learn a little bit about its growth, that kind of thing. All right, I think we're going to move now around to the other side of our Gorgosaurus and look at one of the new specimens that we've collected. So what we're looking at here, this is part of the tail of another tyrannosaur. So these are the tail bones. And if we zoom out and look at our skeleton again, what you're looking at here is this section of the tail. It's near the base of the tail, but it's going along here. So it's about 1/3 of the tail. This is part of a new tyrannosaur skeleton that we're collecting here. This one is from the Judith River Formation of Montana, and it's about 77, 76 million years old. Very, very similar in age to some of the tyrannosaurs in Canada. So this is a specimen we've been collecting for the last 2 years, and we're hoping to collect a little bit more of it and this summer, if we can get out and collect. So if we go into the lab, I'll be able to show you a little more perspective. So this is more of the tail of this skeleton. You can see more of the tail bones here. These are little bones that hang down off the base of the tail called chevrons. This is a picture of what we think is going on with our tyrannosaur. So we've currently collected most of the tail, and the rest of it, most of it is in a block like this, and we think it's all curled up. And this is often what happens to tyrannosaurs after they die, or many dinosaurs after they die, is their head gets pulled back like this. For a long time, people thought that this was because the skeletons dried out, and this is what happens to them after they dry. Yeah, so people used to think that when dinosaurs died, the ligaments all dried up in the neck, all the muscles and things pulled the head back. But now what we think happens, people have done some experiments with dead chickens. And when a dead chicken is thrown into a bucket of water, its head does this same thing, because it's thought that all the strong muscles in the neck usually were holding up this big head. But when it goes into water, the water supports the weight of the dinosaur, so the muscles pull back and kind of curl it up like this. So our tyrannosaur was found in a river deposit. So we think that this dinosaur died, it somehow ended up in a river, and it got curled up like this, and then was preserved in a sandstone. Now, one of the things that happened to our tyrannosaur after it died is that it started to rot. And if you've been out and found a dead rabbit in a field or a dead deer, you'll know that as things rot, they fall apart. Now, the tail, now this isn't a picture of our dinosaur, this is like a sort of a plan. When we found ours, the foot bones had fallen off, and we think we've got an area where there's a lot of ribs. If we go back into the lab, we can see some of these belly ribs. So this is a jacket showing some of the belly ribs, and this is the cleaning up of our tyrannosaur, one of our tyrannosaurs. So these are belly ribs. So these aren't the ribs that you have on a main skeleton like this. They are a special set of ribs that come across the belly region like this, called Gastralia. And we've collected 40 of these from this skeleton. So most of our skeleton seems to be all together, called articulated, but some parts of it have fallen off, including all the belly ribs. So what we think happened was, when the dinosaur died, it was lying on a riverbank after being washed down the river, and then it started to rot, fill up with gas. When things rot, especially inside the stomach blows up like a balloon. And then it got so full of air, its belly burst. And all of the bones that were on its belly ribs blew out like this. And the guts all sort of sloshed around the outside of the dinosaur like this. So this is kind of what ours looked like. So it actually blew one of its arms off. In a minute, we'll take a look in the collections area. You can see one of the arms of this dinosaur that was removed when it burst. So that dinosaur is called Denver's Tyrannosaurus. And if you look in here, these are some more of those belly ribs. So these are the little ribs that protect the organs on the inside. And here, I'll lift this down. This is one of the shoulder blades. So this is what we call the coracoid, and this is the scapula. So on a human, the scapula is back here.
I'm going to just move that label out of the way.
And then just here, this little nook, that's where the humerus, where the upper arm bone fits. So although most of our skeleton is together in the ground, the arm had fallen off when it burst due to rotting. This is another interesting bone. This one is called the wishbone, and it would sit here between the scapulae, the shoulder blades. For a long time, people didn't know that dinosaurs had wishbones, but it turns out that a few had been found, they just been misidentified. Some of the other bones that we have in here. These are some of the first bones that were found from this site. So this was actually the first bone that I found. This is one of the foot claws of a tyrannosaur, of this particular tyrannosaur. And here is another one. This one's slightly larger. So we think this one is from the inside toe, which is called toe 2, and this one is probably from toe 4, the outside toe. We have a lot of other toe bones because this was coming out feet first. So that's one of the tyrannosaurs that we are collecting at the moment. One of the other things that we have a lot of here is tyrannosaur teeth. So this is all material from the Judith River Formation about 76 million years ago. And these are lots of tyrannosaur teeth.
Yeah, so everything that's in here is not just from one animal. These are from what we call a microsite, where there's lots and lots of bones from all the different animals that lived in the area, kind of all mixed together. So imagine like at the bend in a river where a lot of bones might get caught up against a rock, or maybe they wash out on a floodplain. If you're ever hiking around, you see a lot of pile of dead animals somewhere. Hopefully you don't. But you know, if there's a big storm or something. So we have all sorts of different things in here. So there's fish bones. Here's a bit of fish bone. And crocodile vertebrae and hadrosaur bones. Here's the toe of a big duck-billed dinosaur. Looks kind of like a hoof, like a cow hoof. So it's all sorts of things. So it's not just Tyrannosaur material. So we get a lot of teeth, like the Tyrannosaur teeth he was showing you, because teeth are very hard kind of bone. It's a special kind of bone. It's different than the rest of the bone in your body. It's much more dense and strong because teeth have to be really strong to chew and bite all of your food. So they preserve really well as fossils. So we end up getting a lot of teeth. And so the rest of the bones in a dinosaur might be really fragile and we don't find them very often. but we can find the teeth of things. So that helps us know what was living in an area. This is a little tiny piece, but we can tell it's from a tyrannosaur because tyrannosaurs are very special. They're related to birds, and so a lot of their bones are very hollow. And in the vertebrae, in the backbone of a tyrannosaur, there's a lot of open spaces. So even if we just find a really tiny piece of bone, we can still know that it's from a tyrannosaur because of all the tiny little holes in it. They're bigger holes than usual.
A lot of these bones that we've got here, they're all from different animals. And I was talking about teeth because we were talking about tyrannosaurs. So we have a few different teeth in these sites that we can see different features of the teeth on. So this one is a pretty typical tyrannosaur tooth. You might be able to just about see, well, maybe not, the little serrations. If I reflect the light a little bit, you can see the serrations along the edge of the tooth. So that was made for cutting through meat. However, sometimes in tyrannosaur teeth, we see what we call a wear facet, or a place where it's been worn. So this one shows quite well this sort of flat, shiny bit here. That's where the tooth has been worn down. And so how would you wear your tooth out like this? Well, some people think that tyrannosaurs were eating bone. I don't think tyrannosaurs ate bone. I don't think they wanted to, but they did bite through bones. And we see these same kinds of long wear strips, if you like, on animals that bite through hard things like bone, but also sometimes animals that bite through fish scale, bony fish scales. So we have another bone over here that shows what we think might have been happening. Actually, I'll show you another one in here first. Is this megalag?
Yes.
All right. This is part of a duck-billed dinosaur bone, but it's got these tooth marks on it. I think you have there's one of these podcasts coming up later on this week about tooth marks, so I won't talk too much about them, but it is something that we've studied in tyrannosaurs. And these are probably tooth marks made by tyrannosaurs. Here is another bone. This is probably part of the hip of a duck-billed dinosaur. And if I am getting the light reflected right, this little sort of snaking mark here is the tooth mark from a tyrannosaur. So it's quite interesting that when you're in the late Cretaceous period, when tyrannosaurs get really big, we start finding more bones, more dinosaur bones, with tooth marks on them, that we think is possibly because tyrannosaurs, it's not so much that I don't think, it's not so much that they were eating more bone, more that they were capable of biting through bone more efficiently. Their teeth are much wider and stronger than we saw in things like Allosaurus a number of million years before. Now this is shown quite explicitly by another fossil down here. Bang! This one's good for me to get in the light. So this is part of the frill of a ceratopsid dinosaur. And I'm not quite sure. You can start to see it. This is absolutely riddled. It's covered in tyrannosaur bite marks. There's one here. This is actually two. It splits into two here. So this is probably from the front of the mouth of a tyrannosaur splitting into two. There's a curled one here. There's another one here, another one here. There's a really cute one. Where is it? I usually have this the other way around. Oh, here. There's a set of two here, and then there's a little curly one just here. Well, I can't see it right now because I'm in a different light. But all of these marks are probably where a tyrannosaur bit onto the edge of the frill of this dinosaur and scraped and pulled to eat the meat or to pull the head off its body so that it could get at the neck meat. We also have a few marks on maybe this smaller piece. It's quite difficult unless I'm reflecting the light, but all these little lines that you can see, these are lots and lots of tyrannosaur tooth marks. Now, one of the things that I study is I get all these tooth marks, I map them out on the bones, and we don't just look at one, we look at sets. So if we have a whole set of 4 tooth marks, then we know that 4 teeth dragged in the same direction. And sometimes if we're really lucky, we'll see movement in the tooth mark. We'll see where a tyrannosaur bit in, and then the marks will have a zigzag and things like that. So if there's a zigzag in the marks, it means that a tyrannosaur bit and sort of shook. And we actually have 2 or 3 specimens that show that, which suggests that this is real evidence of tyrannosaur behavior. Because you can show anything you want on things like movies. You can talk about it. You can make up stories about tyrannosaurs fighting Spinosaurus and stuff like that. But actually finding evidence for what dinosaurs did, their behavior, is more rare. So we actually have 20 ceratopsian skulls, or parts of skulls like this, that show bite marks from tyrannosaurs. And they show that tyrannosaurs were pulling the heads off of ceratopsians, especially. And in a particular way, they were shaking the food and helping pull it apart. So that's part of what the research that we did. Thought I would get Chomper out if I had Chomper, yeah? So this is a specimen I have on loan right now. It's a specimen that we collected 2009, I think. This is little Chomper, and it's a specimen that I'm working on describing. Now, back in 2009 or 2010, can't quite remember, I think it was 2009. We were collecting a Triceratops. This is when I was at the Museum of the Rocky, collecting a Triceratops specimen. And a couple of people on my crew were walking to the site, and they found some nice bones, and they put them in a bag and didn't mention to me they found these. So a couple of years later, I was in the museum looking through what we collected, sort of random stuff, 2009, and I found a bag and it said, Chomper alligator jaw. And I sort of lifted it up and it was very heavy. I thought, well, that feels nice and heavy. It must be a good sized alligator jaw. So I reached into the bag and I pulled out this. And instantly I thought, well, these tooth sockets, these are tooth sockets. This is part of a jaw. Instantly we can tell it's a jaw, but it isn't an alligator jaw. The tooth sockets are much too square. They're a little bit square, you can see. Alligators have very round tooth sockets. They're almost circular. This was not an alligator. There are a few other small pieces in this bag, like this piece that fits on the end. I know it's quite difficult to tell how big these things are when you're on a camera, but this is quite small. It's about 3.5, 4 inches long, this piece. I looked at this and I thought, is this a little T-Rex? So I took it to my supervisor, Professor Jack Horner. I said, Jack, is this a baby T-Rex? He says, that's what it looks like to me. That's my best Jack impression. So I took it into the lab and I got it cleaned up. And there are only a couple more pieces. But this was the smallest T-Rex that anyone had seen by far. And it was part of the head. It wasn't just little leg bones and toe bones. Those you actually find fairly commonly. It was part of the head, which is really important because that can tell you what species you've got, or it can show how they grow and how they change as they grow. So we went back to this site that year in 2011, 2012, 2012, I think. And we collected more pieces and we started to glue them together. Now we don't have that much of the skull, but we do have a few bones. So this is the other jaw, the other lower jaw. So this more or less is, this is called the dentary. So it's the main bone of the lower jaw. And this looks quite big on this picture, but it's only about 9 inches long. And this is basically the complete lower jaw of this little baby Tyrannosaurus. And it would only have been, its whole head would have been quite small, only about that long. So this is the smallest Tyrannosaurus rex that's known. And we collected a couple more tiny fragments from this site in October of last year. So we're going to be working on describing this specimen very soon. We have a few more pieces just tiny fragments, just these ones here. It's a real shame, actually. These are little fragments of the top of the skull. So there was probably quite a lot of the skull there originally. This is part of here, the frontals, we think maybe. So it's a real shame because this would probably have been a quite good skull many years ago, but it washed out of its mudstone probably a number of years ago, and then fell apart and got broken up. We still have a couple more pieces to glue in place, so it'll look a little bit better, but not too much. I thought I'd show you just a couple more bones, and then maybe people can ask questions if they like. Liz had shown you some of these microsites before, when we get lots of random bits. And it's a bit of a shame because you never get a complete dinosaur from one of these, but you do get interesting pieces. So, this bone is the skull bone of a Tyrannosaur. So this is part of a postorbital. And this big bump that you can see here, when I started this broadcast, I showed you the bumps on the top of a Tyrannosaurus skull. And when they're really big and bumpy like this, we think that they get bigger as the animal grows. So an older individual might have a bigger bump. It also tells us a little bit about the species. So Thomas Carr would tell you that this great big bump here means that this is from a Daspletosaurus rather than, say, a Gorgosaurus. We know that it's 76 million years old, so we think those are the two options. So this is a little bit of another skull that we're digging up. This one's Jack's Tyranno. If I turn it around, it's quite interesting. This was preserved in, when we collected this, it was in lots and lots of little pieces. So we've been gluing them all together. You can see all the little cracks. This was in about 50 pieces, we've been gluing them together. But if I turn it around, you can see it's hollow inside. It's really, really hollow. Tyrannosaurs, a lot of their bones had big air spaces inside, especially the skull bones. This shows it really well in here. I actually have another one of these. Just put this back in its proper place. This one is, we collected, this I think is a lacrimal horn. So this is a little horn from the top of the skull of another Daspletosaurus. So it's got a few more pieces. This one was on its own. It's not part of the skull. It was just on its own at one of our sites. Actually very close to the articulated Tyrannosaurus. I think one of these other things I will show you. This is this big bumpy horn that I showed. This is another part of the same skull. So this is the tip of the snout. So if I rotate it like this, you can see the tooth sockets here. So this is actually the front, it's called the Premaxilla. This is probably another Daspletosaurus. Well, it is a Daspletosaurus because we've got the horn from over the eye. This is another one that we will hopefully be digging up this summer. They're both the same bone. They're the left premaxilla. This one, or Jack's B2, is much, much bigger than this one. This is almost the size of a smallish T-Rex or a medium-sized T-Rex. So when we talk about the age of a specimen, you have the age of the individual. So an animal, or I'm 42, I think, yeah, 42. I'll be 43 in a few weeks' time. I'm 42 years old, but I live basically at time 0 because I'm living right now. So an individual dinosaur lives a number of years, and then of course it may have lived 70 million years ago, 76 million years ago in this case. So if we want to tell the age of an individual dinosaur, then yes, we cut its leg bones, we count the growth rate, and that might give us 20, 30, or 40. Not usually 40. But if we want to know how many millions of years ago it lived, we look hopefully for ashes, volcanic ashes preserved with the dinosaur bones, or as layers above and below. And because we can use the volcanic ash to look for radioactive elements inside the ash, like uranium, and see how much of them has decayed into lead. And that can give us, we can use what's called radiometric dating to figure out how many millions of years ago that volcano was. So when I'm using these two different sets of numbers, the age of the individual dinosaur and the age of the rocks that it comes from, we use different evidence to get that information. They're not really related. Yeah, so this specimen, Jax B2, is a really big Daspletosaurus. This Premaxilla is what we've got. There's a bunch of vertebrae, some bits of vertebrae as well. So this is one that we're hoping to dig up this year if we can get out into the field. This is his nose hole, or his nostril. You can see there's the tooth sockets. There's actually a little tooth inside of there. So I realize I haven't talked all that much about Tyrannosaur evolution. That's kind of not really what we work on. We work on how they live their lives and what we can find out and what sort of evidence we can discover that tells us how they live their lives. So that's a little bit about what we do here on Tyrannosaurs, I suppose. Mostly I work on horned dinosaurs, and Liz works on duck-billed dinosaurs, but we just happen to have, we have a number of Tyrannosaur sites that we're working on right now because we found a bunch of them over the last sort of 5 years. So we just happen to have a lot of Tyrannosaur bones. I don't know, is there anything else to add?
Now we can move on to questions. I saw a lot of questions popping up, if Becky's been keeping track of them.
How did you find out that female T-Rexes were bigger than males?
Well, people used to think that you could tell a female T-Rex from a female Tyrannosaur from a male Tyrannosaur, and the evidence suggested for that was one of the Chevron bones. So one of the bones at the base of the tail, I can show you on this little Sauronatholestes skeleton that we've got here. This cast, these bones that hang down here at the back of the tail. It had been suggested that females may have had a slightly smaller bone there to allow the eggs to be laid more easily. And that had been used to suggest that we could tell males apart from females. But that has been found, because you might see that in alligators, but that's been found that it doesn't actually hold up. We don't currently have, we can tell male and female dinosaurs apart sometimes by looking at their bone histology. So if the inside of the leg has a special kind of bone inside called medullary bone, then we can tell males from females. And that has been done for one T-Rex, B-Rex, it's the only one.
Yeah, so this is a cow bone, not a T-Rex bone, obviously. But you can see the hollow space inside. So that's where the bone marrow goes. That's the medullary cavity. And birds are special that when birds are about to lay eggs, they need a supply of calcium. And bones are made of lots and lots of calcium. So birds add some extra bone in here right before they're about to lay eggs. And it turns out the T-Rex did the same thing. So if we're really lucky and we get a T-Rex fossil right when it's about to lay eggs, we can find that special bone inside and we know for sure that that one was a girl. But we don't always get that lucky, and it's still being researched. So there are people working on it to try and identify more T-Rexes, whether they were boys or girls. But it doesn't work for all dinosaurs. It doesn't work for all animals. So most dinosaurs, we don't know whether they were boys or girls.
Do you have to get permission to dig at a site?
Yes.
Yes, and it depends on who owns the land. Most of what we work on is from public land. So it belongs to the people of the United States, and various different government bodies in Washington, D.C. Give you permission. So I have to send a letter to the Bureau of Land Management, for example, that says I would like to go and look on this spot of land. And then they look through my history and make sure I haven't caused any fossil crimes and things like that. And then if I look pretty good, then they'll send me a permit that allows me to go and look for dinosaur bones on public lands. If it's private land, if it's owned by a private landowner, like around here, lots of ranch owners and things like that, then you have to get permission from the rancher. But to collect on public land, you usually have to be associated with, you have to be associated with what we call a repository. So that is a place where these public-owned fossils can be stored forever, so that we can always have them on display or always be able to study them So you do need permission to go onto wherever land you go on, unless you own it.
Yeah, whoever owns the land has control over it.
Have you ever found bones from other dinosaurs within the body cavity of Tyrannosaurs?
I'm not sure if that has happened. I'm not sure if there were gut contents of any Tyrannosaurs.
Not yet, but we're looking. We will definitely look at our Tyrannosaur.
There've been a few. I mean, our Tyrannosaur, we don't expect it because we think that its belly burst as it was rotting. So if it did have any gut contents, they were sprayed all over the place around the where the skeleton was preserved.
Yeah.
And
you have to be careful too. Even if you do find bones of another animal inside the body cavity, so like with this little guy, even if we were to find other bones in here, they may have washed in after the animal died. So there's a hadrosaur specimen, a duck-billed dinosaur, and they found a whole fish up inside its belly. And so they thought at first, did it eat a fish? Duckbills don't eat fish. But imagine this dead duck-billed dinosaur lying in a river, and its belly makes a nice little cave, and that fish swam into the cave and was just hanging out inside the duckbill because it was a good place to live. So the duckbill didn't eat it, but it was found inside the belly. So you gotta be careful.
There have been some Tyrannosaur poop pieces found, or what people think is Tyrannosaur poop. It's quite difficult to prove. And they had little chunks of bone inside and some other things preserved. So that's kind of like gut contents, but it's a little bit later in the whole process. But I don't think there have been any Tyrannosaur skeletons found with gut contents.
Is Albertosaurus in the Tyrannosaurid family, or is it separate?
Albertosaurus is a Tyrannosaur. Yes. Our skeleton outside is labeled as Albertosaurus, but it's actually probably not Albertosaurus. And the reason why is, I think in the 1920s, there were a number of Tyrannosaurs named Daspletosaurus, Gorgosaurus, Albertosaurus. And for a while, we used those different names. And then people thought, well, Gorgosaurus and Albertosaurus are probably the same thing. So people stopped calling things Gorgosaurus. And that ran all the way up until, I think, the early 2000s, when we decided that Gorgosaurus and Albertosaurus were actually different species. And there's very good evidence for that. Albertosaurus is only known from the Horseshoe Canyon formation of Canada. And the Horseshoe Canyon that has Albertosaurus in it is about 73 million years old, whereas Gorgosaurus is actually about 77 million years old. So they're separated by 4 million years, so it seems likely that they're different species. We just called them the same thing originally because they're both kind of lightly built Tyrannosaurs. They're not as heavily built as something like T.rex or Splendosaurus. So yeah, our skeleton says Albertosaurus on it, but it's actually a Gorgosaurus because I believe it's based on bones that we would now call Gorgosaurus from dinosaur population.
On the histology slide where you had all of the rings with the years written on, there's a lot of little lines with the dots. How can you tell which ones are the year rings and which are not?
So to find the growth rings in a dinosaur, what the growth ring is showing is a time, probably in winter, we assume, when the animal briefly stopped growing. So you're looking for one solid, unbroken line that represents the stopping of growth. And then in the spring, when food was abundant, the animal would start growing again. So you have to follow all those little lines, and most of them don't go very far. But the true lines, what we call them lines of arrested growth, lines when growth stopped, it'll be a faint line, and it does go all the way around the bone without breaking.
From the bloated Tyrannosaur site, have you found any skull or teeth bones yet?
No, we haven't. But usually when they're curled up like this, the skull is typically stuck on the end of the neck. And our problem is that, as you saw, well, the big tail piece that we saw out in the exhibit, that was in a relatively soft sandstone, and the belly ribs are actually in a relatively soft sandstone too. but the rest of the skeleton is in a really hard sense. And we actually have to lift it all out in one go. So if we look at the skeleton, all of this area here is in a big concretion. And the only bits that are sticking out of the concretion are the foot and the tail comes out like that. I have a photograph of that right now. So we haven't found the head yet, but when we've been trimming down the concretion, we find the edges of some of the bones sticking out on the edges. And kind of fortunately for us, if the head is there, it will be right in the middle, more or less. It's sort of the middle and to the top. It will be quite away from the edges. So I expect it will be that, because the shape of the concretion that we have actually matches the body shape. And the edges, like for example, where we expect to see the ribs, we see little sort of cross sections of ribs sticking. That's called Denver's Tyranno, that one. That's articulated. The other ones I was showing you, skull bones, those ones are disarticulated, so we don't know how much there is going to be of those. But we are hopeful that the head will be there on that articulated, but we don't know that.
Did anything eat T-Rex?
Did anything eat T-Rex? Well, that's a quite difficult thing to test or a difficult thing to investigate. Certainly there have been tyrannosaurs found with bite marks on some of their bones. Sometimes we find tyrannosaurs with, quite famously, a lot of tyrannosaurs have heel bite marks on their faces, which suggests they may have fought each other, or maybe this was rivals competing for mates. That's different because they're not eating each other, they're just scratching the bones and then the bones sort of heal. But there have been some T-Rex bones found. I think they were T-Rex, but they could have been other tyrannosaurs, I don't quite remember. But things like leg bones that show marks, tooth marks on, suggesting that another dinosaur came along and ate the muscle and the meat from that dead tyrannosaur. And given the size of those marks, and I believe that they're from North America in the late Cretaceous, it was probably another tyrannosaur. So some evidence for cannibalism. Although cannibalism is actually more rare than you might expect. Most animals have a sort of innate sense of not to eat their own kind. And in fact, most carnivores will avoid eating. They'll avoid eating the meat from other carnivores somehow. We don't quite understand how that works, but it's not smart to eat meat from carnivores. People that do it, it's not a smart thing to do, because carnivores build up toxins because they eat lots and lots of plant eaters. If you're a plant eater and you eat grass that's been contaminated by something like, these days we might think of any kind of toxic waste, they only get a little bit of it, so they don't get building up in their system. Or lead, for example. Lead is a quite common one. You can eat lots of grass and you won't get that much lead. But if you eat the animals that eat the grass, you get all the lead that they got, and then from every single one that you eat. So we get a buildup of toxins.
Yes,
So,
most animals eating grass don't have that much lead, though. Don't let them scare you. Just an example.
right, but this is why you get buildup of toxins in predators more than you get it in herbivores. So that doesn't just apply to lead and things that humans have introduced to the environment, but it applies to all sorts of other ancient toxins as well. So generally speaking, carnivores don't eat other carnivores as much as you might.
What are your favorite dinosaurs?
Not Tyrannosaurs. My favorite dinosaurs are ceratopsids. So like Juvie Trike 3 here at the back, this is one that I collected in 2008, I think, around like 2008. That's a copy of one at the Museum of the Rockies. I work on specifically the long-horned, long-frilled ceratopsians called chasmosaurians, things like Pentaceratops. I suppose they're among my favorite dinosaurs. These days, I kind of like whatever I'm working on at the moment. So I really like Albertosaurus at the moment. Weird little insectivorous guys with just like one big claw on their hands. That's kind of one of my favorites right now. And Leptoceratops is a favorite right now.
What is your stance on Nanotyrannus, and does the Dickinson Museum have any bones?
Well, my stance on Nanotyrannus is that it is most likely that Nanotyrannus is a juvenile T-Rex. The original Nanotyrannus, that's the one at Cleveland Museum. What some people call Nanotyrannus at the Burpee Museum, Jane, I believe that's also probably, it's most likely to be a juvenile Tyrannosaurus Rex. We can never prove such things, you see, and that's part of the problem, is that those both of those animals, well, Jane we know is young because it has leg bones preserved, so we can look at the leg bones. The original Nanotyrannus, if you like, in Cleveland, is only a skull, so we can't cut its leg bones to tell whether or not it's mature. So it's kind of like we're not really sure about that. But I think the most likely explanation is that they are young Tyrannosaurus Rex. And I probably have a more extreme view on that than most people. I think there's a few Tyrannosaurs that are misidentified. There's a very good chance that there are some, maybe some of your favorite tags that perhaps aren't as real as we would like them to be. Maybe they're juveniles of others. But we can only find that out if we actually cut up more Tyrannosaurs. And that's actually a big problem, that many museums, they consider fossils to be precious, and we really need to be cutting up leg bones of basically everything, especially nice skeletons, where we have a whole skeleton with a beautiful skull. They're the most important.
All right, so we've all seen the movies where T-Rex stands and lets out a blood-curdling roar, but what are your thoughts on dinosaur vocalization?
It's a very difficult thing to test. There was some suggestion that some of the duckbills, which I guess I'll let Liz answer about that, but they have these crests on their head, and some of those crests were hollow, so there was some suggestion that may have been used to make noises, like a trombone, Parasaurolophus. It's difficult to say with things like Tyrannosaurus. Most animals that live on the land, at least, do make noise of one kind or another. And social animals that live in groups or interact with other members of their own species quite commonly, often make more complex sounds than animals that live on their own. So we might expect, if Tyrannosaurs were social, then likelihood is that they made perhaps a range of sounds. I'm not saying they had a language, but they might have sounds for go away or hello and that sort of thing. It's like your cat, that kind of thing. Well, their cat's actually not social, really. But if they lived on their own mostly, then they probably didn't have as many different vocal noises, because who would need to speak? Anything to say about that? It's very difficult to prove. Well, difficult to test, never mind.
It's because the body parts that make sound are not made of bone. They're made of soft tissue and things like cartilage. So, like, if we were to get really lucky with the most amazingly preserved T-Rex ever, we might get those cartilage pieces, and then you might be able to look at the structure of its throat and predict what kind of sounds it could make. But we just don't have those fossils. So, yeah, they're related to birds, they're related to alligators. So, they made a noise somewhere in between.
Bigger animals tend to make quite low sounds. Smaller animals make quite high sounds. And, Tyrannosaurs probably had deeper voices when they got larger, but other than that, I don't think there's really much there's probably not much use that you can really find out. They probably made sounds, and if we found out exactly what sound they could make, it still probably wouldn't tell us.
On the tooth that you held up that had the wear facet, would that have been caused by the other teeth on the opposite side of the mouth?
The thought is that those sorts of long wear facets are caused by biting through bone rather than from tooth-on-tooth contact. That was a particularly nice wear facet, which is why I was showing it to you. But when T-Rexes, what I think Tyrannosaurs are really doing, I don't think that they want to bite through bone and eat bone. I think this whole idea of Tyrannosaurs biting through pelvises and biting through leg bones, you don't want to bite through a bone. When you bite into a bone, it hurts, right? You don't want that to happen. And I think Tyrannosaurs are very similar, but they did want to eat the meat. And what makes Tyrannosaurs different from most other carnivorous dinosaurs is their ability to pull a carcass apart. I'm not calling them scavengers, but they have big, robust skulls, they have robust teeth, and to me, they look like they're made for what we might call shake feeding, that their teeth are resistant, they're strong, so if they get pushed side to side, they don't snap. So they could bite into a carcass and just pull it apart and shake it to pieces. And we see evidence of that in the tooth marks that we see on some of the frills, like the flat parts of ceratopsian skulls. We see evidence of shaking, of pulling, and just violent pulling apart of carcasses. And that's what I think makes Tyrannosaurs exceptional, that they were exceptionally good at processing a great big carcass of a dinosaur. Now, whether or not they killed that dinosaur, we can't know. I suspect they probably did go out and kill things, but ultimately it doesn't really matter. If you either find a carcass or you killed it, you've still got to pull it apart to eat it, and that's the challenge. As any hunter will tell you, how you efficiently cut the meat off a carcass is quite a skill, and it takes the right tools. And T-Rex, it had the tools. It's made for dismembering carcasses in a way that no other dinosaur, not even the big ones from South America, etc., they're not made in the same way that a Tyrannosaurus. So I think that's kind of where I'm going with that branch of research. I can't even remember what the question was, but I've rambled so far.
Why was Tyrannosaurus so keen on getting the neck meat that he would rip the skull of a Triceratops off?
Well, it's slightly backwards, if you like. When we were looking at all these Triceratops skulls at the Museum of the Rockies, John Scanella there studies Triceratops, so we collected lots of Triceratops for that project. And we started seeing lots of tooth marks on the skull bones. So we started looking a bit more detailed for them. And the first place that we started seeing lots of tooth marks was on the ball on the back of the skull. So if I just bring, this is the back of a skull, and this is the ball that fits into the neck. We started seeing lots of tooth marks on the ball. And then we started seeing lots of tooth marks on the edges around the frill. So we started to ask ourselves, well, why are these marks occurring where they're occurring? And many of the marks were what we'd say longitudinal, so they were going up like this. So they showed pulling in this direction. And we actually had marks that showed twisting too. So we hypothesized from the distribution of the marks, from where the marks were placed, that tyrannosaurs were pulling the heads off Triceratops. So the big marks around the frill, which were big, they were deep gouges most, that they were grabbing hold of the frill and pulling it violently, and then they would eat the neck meat, which when you think about an animal that has a head of this size, it needs a big fat neck to hold the head up, which means it needs lots of big neck muscles. And the fact that we had marks on the what's called the occipital condyle, the ball, meant that it was scraping the meat off that part of the skull. So, I mean, we don't actually know that tyrannosaurs were removing the head to get to the neck. I think that it's just part of the overall pulling the carcass to pieces. And an interesting part of this is that
It's one of the late stages of eating
the
carcass. It's, you know, it's not the best meat. It's not the easiest to get to.
They probably would have eaten the leg meat and belly meat and stuff like that earlier. We also get lots of tooth marks in the nose area of a Triceratops, which is quite interesting. But when you look at the nose of a Triceratops, I wish this had more wheels. This is one of the last places. This would have had a quite fleshy nose, and we often get tooth marks around here too. So maybe at the very end, if a carcass has been lying on the surface for a long time, lots of different carnivores have taken the best meat. There might be a little bit of meat left on the nose, and so we see little scrape marks where tyrannosaurs have been eating nose meat as well. So I know I have to publish a lot of this research, but we have lots of different marks showing different kinds of feeding in different areas of the skull. Now, it's not so much that the skull is the best meat. I think this is what's called survivor bias. If you look at the frill, it's full of lots of flat surfaces. If you ever try, I showed you some other bones before that had tooth marks, and if the bone is curved and round and drag a tooth across it, you only really catch the edge of the curve, so you can make a little short tooth mark. But if you wanted to make a long mark on a round bone, you'd have to scrape all the way around the bone. So you're not going to get complicated tooth marks on leg bones, ribs, things like that. You just get like a little notch on the edge. When you have a big flat surface like a frill, it's like a canvas for a painter. You can scratch and scrape. If you make a long mark, you'll preserve the whole length of the mark, and that's actually what we see in the best tooth mark specimens. We see long marks crisscrossing each other and all sorts of things. So you can see more complex movement of the tyrannosaurs as they pull apart the carcass. So it's not so much that, I mean, I think they are going for the neck meat, but it's not that they prefer the neck meat. It's probably just that that's an area that we can actually see the scavenging behavior preserved more easily. If they scavenge the rib cage well, it's going to get crunched up and lost. If they scavenge the neck, the head might hold together. These are big, tough bones, and no one wants to eat that, believe me. So this is going to be preserved better than a rib, that sort of thing. I kind of ended that badly, but
Yes.
it's preservation bias as well.
Have there been any T-Rex nests found or eggs?
That's an easy one. No.
So you kind of touched on this, but we'll just ask it anyways. Is Giganotosaurus a tyrannosaur?
Giganotosaurus is not a tyrannosaur. I can't remember exactly which group it's considered part of these days. It's a Allosaur grade, or perhaps it's from South America, Giganotosaurus, and so the dominant carnivorous dinosaurs in South America are actually quite different to those in North America, and more similar to some of the African kinds. But it's not a tyrannosaur. It had quite slender, thin teeth. I think it's a Carcharodontosaur. I can't remember the names of those groups. Liz is looking it up, but no, it isn't a tyrannosaur.
Do you believe that T-Rex hunted in packs or alone?
Pack hunting is very unusual in modern animals. I think that a lot of what we think about carnivorous animals is biased by the fact that it's very easy to film lions and things on the Serengeti. And they're also very interesting when they live in groups. So we see a lot of that on television. But actually, most carnivores, first of all, they don't hunt in packs. And most carnivores also aren't pursuit predators. They don't catch their prey by running fast after it. Most carnivores catch their prey by sneaking and pouncing, or what we call, damn it, I don't know the name now. What do you call a non-pursuit predator?
Ambush.
An ambush predator, there we are. Got my words. They're mostly ambush predators that they will surprise their prey, if you think about how crocodiles are, things like that. So do I think Tyrannosaurs hunted in packs? Well, you know, there is a bone bed of a group of Tyrannosaurs, Albertosaurus, up in Canada. So some people would suggest that might be an example of them at least being preserved dead in the group. But that could also have formed a number of ways. It's quite difficult to preserve a hunting group of animals all together in the same place. I'm not saying that they didn't hunt in groups, and I'm skeptical that we can know that based on any of the current fossils that we have. And the same, I think, applies to little raptor dinosaurs. I don't think that's very good evidence that they hunted in groups. They might have done, but it's one thing to hypothesize about something, it's another thing to be able to test that hypothesis. So right now I suppose we don't really know. I don't think anyone really knows.
What kind of schooling do you have to go to become a paleontologist?
These are the sorts of questions that there's a few different answers to. To work in a museum like this, or to be a professor at a university, you have to go through a lot of schooling. You have to do your high school, and you have to get an undergraduate degree from university, and then usually you'll go on to get a master's degree and possibly a doctoral degree, and that's many years in college. But that doesn't mean that you can't be a paleontologist if you don't have those higher qualifications. I have many friends in England who are the best dinosaur collectors that I've ever met, and they don't have degrees in dinosaurs, they don't have degrees in paleontology, but they are absolutely excellent at finding dinosaur bones and identifying them. And anyone can write a research paper about fossils. If you've read enough books and you know enough, or you found something new and you know you found something new, then you can work on it. So there's those sort of two different ways of thinking about it. Yes, if you want to be a professor studying dinosaurs at a museum or in a university, then you'll have to go through lots of college. But you can take part along the way. I have volunteers in my laboratory who are local people who just like fossils, who get to work on fossils in the lab. So it really depends on what you want to do.
What are your thoughts on juvenile or adult T-Rexes having feathers?
Do you know, there's a part of me that doesn't really like the idea of Tyrannosaurs with feathers, and that's just purely personal. I think there's some evidence to suggest some of them may have had a bit of fluff. I think the Chinese form may have had some fuzz on it. And I think there's a very high likelihood that young dinosaurs especially might have been covered in fluff, a bit like little baby chicks that we see today. But there are some patches of skin preserved from large tyrannosaurs, and those patches of skin don't show any evidence of feathers. So we think at least the large tyrannosaurs from North America probably didn't have feathers. But again, we don't have that many patches of fossilized skin from Tyrannosaurs, so it's possible they might have kept like a little crest or something like that. But when they got very large, they probably didn't need feathers to keep warm, because they were so large, they probably kept plenty warm just by being large. So at that point, perhaps feathers wouldn't be needed for insulation.
How old is the oldest aged Tyrannosaur? Like how many growth rings did it have?
Do you know, I think that's something that we don't have a proper answer for right now. When we actually get the age of our Tyrannosaur that I showed you that we're cutting up, we're going to run a little competition where people have to guess how old it was. And then whoever gets closest to the right answer can win
The short answer is we don't know yet, but our friend Dr. Holly Woodward in Oklahoma is studying that right now. And so she's looking at a lot of different T-Rexes, and stay tuned for the answer. She's working on it.
There have been some studies done in the past on this, but the problem with that is that a lot of the bones that were cut up are things like ribs, and we know that you shouldn't be using ribs to study the age of dinosaurs, because ribs change shape so much as the animal grows. They don't give you a good piece of evidence. So right now, I would say we don't have a very good handle on how old these dinosaurs are.
Do you know any of the lesser known behaviors of tyrannosaurs that we can deduce from fossils?
That's a tough one. What do we not know about much, but we know a little bit? I mean, behavior is very difficult. We don't have any good tyrannosaur trackways, for example, so we can't look at how fast they could run based on tracks. The evidence that the tyrannosaur speed, for example, the speed that they could run is based entirely on looking at their leg muscles and hypothesizing based on that. I think there's one tyrannosaur footprint from New Mexico, but one footprint doesn't tell you anything. You need at least a few of them in a row to see how fast an animal is moving. So we don't really have that information. It's a tough question, that. I mean, what sorts of things could we look at? Well, there's been some work done on the different isotopes, different chemical elements in their teeth that can tell us a little bit about how much these animals may have wandered around the landscape, that kind of thing. Those sorts of studies are just starting to be done, and I think there's a lot of information that we might be able to get from what's called isotope studies. So they look at things like carbon, nitrogen, oxygen in the teeth, and particular ratios really are different depending whether you live in the mountains or whether you live on the plains, whether you drink from rivers, lakes, things like that. And as we gather more information from more teeth, we might actually be able to profile tyrannosaurs as living in a particular way compared to, say, raptors or one of the mimids or other fairly closely related carnivores. And what's more interesting, actually, is that we've just started to be able to study what we call heavy elements. So not just carbon and oxygen, things that are quite light, but things that are heavy, like iron. And those might tell us even more. So I think that in terms of tyrannosaur behavior, that's actually a really interesting avenue. It's just starting to open up. There's a really cool paper published about a month ago.
Yeah, there's some really cool chemistry stuff that you can do that people are just getting into.
All right, so we're going to end with, how rare is it for you to find a juvenile or baby Triceratops skull?
Not as rare as you would think.
I suppose there aren't that many that have been found.
What's this one called?
This one's called Juvie 3 because I found 3 that year, but this was the nicest. I mean, Triceratops is a very common dinosaur. I mean, Barnum Brown said he walked over 400 Triceratops in the Hell Creek, and I believe it. I'd collected over 100 with the Museum of the Rockies and here, and we didn't collect every one that we found. We collected the ones that would tell us something new or good or well preserved. So juvenile Triceratops, finding odd bones from juvenile Triceratops isn't that rare. I would expect to find a few if I was out for a full season. But finding a whole skull like this.
It was all in pieces. It got put back together. It was originally all disarticulated and spread out over a big area.
It was disarticulated and spread out, but this particular one is almost complete. The only bones that were missing were the back of the lower jaw and some of the spikes around the edge of the frill. We only had a couple of those. But most everything else in this skull is real, or is copied from the real bone. It was fallen apart, but we actually found most of it. I mean, how rare are they? Yeah, they're one of the more rare things you find, but they're not as rare as things like armored dinosaurs. Ankylosaurs are very rare in the Hell Creek, or good little raptor skeletons, things like that. Those are more rare than baby Triceratops, or young Triceratops, already a baby. But you find bits, little bits of frill and stuff quite commonly. I'd expect to find those, a few of them a season. And if I'm really out prospecting, maybe one a week, a couple of weeks, something like that.
Okay, I think that's pretty much wrapping it up here. Thank you so much for taking the time to answer the copious amounts of questions. Everybody loves dinosaurs, and definitely loves T-Rex.
Yeah, it's great. I'm glad so many people joined us. Thanks.
Okay.
You're interested in what we do.
Okay, Clint, you want to let us know what tomorrow's topic is? I don't know if you have the list up there.
Yep. So tomorrow we're going to be talking with Dr. Andy Farkey, and we are actually going to be talking about another baby dinosaur, which is good to end talking about baby Triceratops. We're going to talk about a baby specimen of the duck-billed dinosaur Parasaurolophus that he helped discover a few years ago, and everything that helped them learn about Parasaurolophus. So join us tomorrow and we'll head into that exciting topic.
All right. Well, thank you so much, and take care out there. Stay safe and have a wonderful rest of your day.
Thanks, you too.